The golden ratio, the divine proportion, phi. What is it exactly, and what are its mysterious properties? This video hopefully will begin to answer that question. So first let's start off with what exactly is the golden ratio. Take a line segment and divide it into two parts. Let's call them x and y. The golden ratio phi is defined as the ratio between the whole segment and its larger part, such that that ratio is equal to the larger part divided by the smaller. In other words, the ratio of this whole piece to this one is equal to the ratio of this large piece to this smaller one. And this ratio is equal to 1 plus root 5 over 2, which is approximately equal to 1.618. The first question you might want to consider is, where does this value come from? Alright, so for x and y, let x be phi and y be 1. This way the ratio x to y is equal to the golden ratio which we're looking for. And it's fine to just let one of the values be a constant, since what matters is the relationship between the two numbers and not the numbers themselves. So phi by definition would be x plus y over x, which is equal to x over y. This becomes, with our new assignments phi and 1, phi plus 1 over phi equals phi over 1. We want to isolate phi. That's the ratio we're looking for. So you can just take a cross product, multiply this across, 1 times phi plus 1. Phi plus 1 equals phi squared. And this just becomes a simple little quadratic. And to solve it, you can use the quadratic formula. I'm not going to write it all out, but when you plug in all the values, b is negative 1, a is 1, c is negative 1, you get phi equals 1 plus root 5 over 2. And that's where the value comes from. One of the first observations that can be made concerning phi is that it is a nested fraction. In other words, phi equals the square root of 1 plus the square root of 1 plus the square root of 1 plus forever. Now there's a nifty little proof for this. You start out with the value of phi, which I just proved. Now you square it. Phi squared equals 1 plus 2 root 5 plus 5 over 4, which is equal to 6 plus 2 root 5 over 4. You can take out a factor of 2. 3 plus root 5 over 2. Further break that down, which is equal to 1 plus root 5 over 2. Now this is phi, so phi squared is equal to 1 plus 5. That's interesting. Take the square root, and you have phi equals the square root of 1 plus 5. Now you can just substitute this value for phi. So phi equals the square root of 1 plus square root of 1 plus 5. Substitute again. And you'd go on forever, and there's the proof. The next thing you might be interested in learning is how to construct the golden ratio. You can do it in 3 simple steps. First, you construct a square of unit 1. Then you connect a midpoint of the square with an opposite corner. And finally, you draw an arc with the newly formed diagonal to form the height of your golden rectangle. Now let me show you. I cheated a little bit here. I actually drew a square without constructing it, but it doesn't matter. It's a simple procedure. The square is unit 1. First, you take a midpoint of a side and connect it with its opposite diagonal. Let's do that. Whoops. So here I'm finding the midpoint, just right here, and then you connect it, the opposite diagonal. Now what does this do? Well, by bisecting the side, you create a segment with the length 1/2. This is still length 1 because it's a square. Now you have a right triangle with legs 1 and 1/2. What this does is creates a diagonal with root 5 over 2. Now remember, the golden ratio is 1 plus root 5 over 2, or 1/2 plus root 5 over 2. So you need to take this segment and add half to it. So here's what you do. This is 1/2 right here. That's the segment you're going to add to it, just by extending your root 5 over 2 segment. Third and final step, draw an arc and extend your segment. So now here you have a golden rectangle, 1 and root 5 over 2 plus 1/2, or 1 plus root 5 over 2. 1 to 5. And you can form a rectangle like that, a golden rectangle. One of the interesting properties about the golden rectangle is the way it allows for fractal patterns, infinitely going in and infinitely going out. So here is a golden rectangle. The ratio of the length to width is 5. If you take out a square, the ratio of the length to width of the newly formed rectangle is also 5. And you can keep going, taking out squares and still getting golden rectangles. Now conversely, you can add squares to a golden rectangle and still get the golden ratio 5 between its side lengths. This is due to the very nature of 5. It is by definition. And you can keep adding lengths and forming a fractal pattern. And if you draw semicircles inside the squares, you get what's called the golden spiral, which looks a lot like the shell of a snail or something. Very interesting. And this pattern can be done with triangles that have the golden ratio, or pentagrams, lots of different geometric shapes. In the interest of keeping this video brief, I'm going to show you just one more property of the golden ratio, and it has to do with the Fibonacci series. So the series are simple recursive pattern. You start out with 1 and 1, and the next term is the sum of its two preceding terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. Now if you take the ratio between 1 and 1, you get 1. If you take the ratio between 1 and 2, you get 2. Between 2 and 3, the ratio is 1.5. The next ratio is 1.6 repeated. Then 1.6, then 1.625. Now what's interesting is that the ratio between two consecutive Fibonacci numbers approaches 5. In other words, 5 is the limit of the Fibonacci, of the ratio between two consecutive Fibonacci numbers. I'm not going to prove this, but I am going to link to a site which has a very nifty little proof. So that's it. Thank you for watching. All about the golden ratio. Very interesting number. Shows up in art, mathematics. Shows up in ancient Greek architecture and the Egyptian pyramids. Very interesting number.